Hello, everyone, and well, thank you for joining us on this evening. We are trying something new, so apologies in advance if it fails. But since we're trying something new where we have live coding, we're just going to give just 2 or 3 more minutes because I don't want us to lose people. But in the meantime, make sure you have a Kaggle.com account. Look at the instructions for the webinar. And there's always the question option on GoToMeeting, but it's very difficult to paste screenshots or get live help. So we're using Slack. We have a couple of people who've joined there, and we're just using that to make sure that you can get instant help. So like I said, we're gonna wait just a little bit more for people to join in, but I'm pretty excited about this. Okay, if you're joining us, we are just giving everyone a few minutes because we don't want to leave people behind. Just make sure you have a Kaggle.com account and join the Slack channel just to get help in case you're stuck or help others. That's how the live coding really works well. So I'm gonna give you maybe 1 more minute. So we're gonna start at 5 p.m. Kenyan time. Okay, so we're gonna get started now. This is our February Journal Club, and it's a hands-on session for non-technical beginner with model building using Kaggle. Big words, but what it says, you don't need technical skills to get started on this, and hopefully you're gonna learn something. And I'm pretty excited, and if people like this format, we're gonna have a couple more, not just on Kaggle, but using Fast AI and many other things. So I'm pretty excited about this, and I hope you provide feedback about it. Just feel free to type on Slack or type in the questions. So today I would like to thank the AI Journal Club Advisory Council. I mean, these guys are phenomenal, and it would be really difficult to do this without their help. I would also like to extend a special thank you to residents who've been reaching out that they want to be the next counselors. And, I have a couple done. It has been phenomenal. And we will, hopefully over the next couple, we'll have them run over the sessions. And as we start to fade away in the background of old age beyond fellowship. But, if you're interested in sort of taking this over, please reach out. I mean, it's been a phenomenal experience for me, and I think to see new faces would be pretty amazing. So for this journal club, you need a Kaggle.com account. I mean, it's really easy to set up. Just make sure you have that. And if you don't think you'll be requiring help, you should be fine. But if you'll need help, I would highly encourage you to join the Slack channel. You can post a picture there. There's a general channel that you can just post for help. And yeah, and so our guests are all PGY 5s, from Brigham's, and I'm really excited and really want to thank them for their leadership and for joining us. I will let them introduce themselves and take over the Journal Club. Thank you. Michael, do you want to go first?
Oh, sure. Sure. I don't know if Walter. Yeah. Okay. Hey, everybody. My name is Michael. I go by Travis. My middle name. I'm a, like Judy said, a PGY5 at Brigham and Women's. From Texas originally, med school in New York. I will be a neuroradiology fellow next year at UCSF, and I am a total novice to this universe. I'm about as untechnical, non-technical as it gets. So if you feel like you need things to be sort of dumbed down, I'm probably the best person to ask because Walter and Cutie both have a much greater knowledge base than me. So please feel free to reach out to me on Slack for non-technical questions, maybe.
Okay. Dr. Magodia?
Hi, so this is Kirti. I'm also a PGY5 resident at Brigham and Women's Hospital, and I'm really lucky that this year I had the opportunity to work with both Walter and Travis on research related to AI and machine learning this year. I grew up in California. I went to Berkeley and I did mechanical engineering, so not directly related to machine learning, but still kind of set me up for some of this theory. And I'm really interested in seeing how to put all of this together for the future. Okay. Also looking forward to helping everyone on the Slack channel.
Okay, thank you. Catherine, do you want to move to Walter so that he can introduce himself as he presents the Journal Club?
Okay, so hello everyone, I'm Walter Wiggins. I'm also PGY5 at Brigham and Women's Hospital. Travis, Kirti, and I are all part of a newly created data science pathway in collaboration with Brigham and the MGH Brigham Center for Clinical Data Science, so hence the background on the slides here. I want to thank you all for joining us today, and I'll spare you too much detail on me, but suffice it to say that I do have some programming experience, but really all of this experience in AI and machine learning has been borne out in my free time over the past couple of years trying to teach myself some of this stuff. So hopefully I can help anyone out there who's interested in learning more of the technical side of machine learning jumpstart your training today. So we don't have any relevant financial disclosures. I am an unpaid contributor to Fast AI and a 2019 Fast AI Fellow, so we will talk a little about Fast AI, but most of this is being done in Kaggle with Keras on top of TensorFlow, and if you don't understand anything of what I've just said, it doesn't really matter at this point. But just to say that, you know, we will talk about some other options for furthering your training as you go on. So learning objectives here, I want to make sure that everybody here, first and foremost, gains some familiarity with deep learning and how a model is trained. The best way to learn is by experience, so this is a hands-on module. Second, you know, some of these learning objectives, we may not have time to get too much of the theory, but just to understand that it's important to organize your data into training, validation, and testing data sets so that you can preserve some of that data for evaluating your model as you're training and testing it once you're done with training to make sure that you're not biasing too much the sample that you're testing on, and we'll talk about that a little more later. And then hopefully at the end you can also identify some basic medical imaging tasks suitable for deep learning. So what we're going to do is we're going to create a classifier of radiographs. So we're going to take a data set that has some chest x-rays and some KUBs, and we're going to train a network called the Inception V3 network, which is a neural network architecture developed by Google to be able to predict whether or not an image that's fed into that network is either a chest x-ray or a KUB. And we're going to do this in Kaggle. Now, just to briefly mention this so that it doesn't get missed if we run long on the coding part of the session, I just want to say that, you know, a couple of resources that I've found to be very good for independent learning over the years. First of all, tutorials are free, and there are many good ones out there, but if you want to take a more efficient path, more focused learning, I recommend the books Python for Data Analysis by Wes McKinney and Deep Learning in Python by Francois Chalet. He's the creator of Keras and works for Google, and so they've folded Keras into TensorFlow now, and Keras is the library that we use to do deep learning in this module. And we'll explain a little bit more about that as we go on. And then once you're finally comfortable with programming in Python, the language that we'll be using today, you're probably ready for Fast AI. And if you haven't heard about Fast AI, it's a course that's run by Jeremy Howard and his partner Rachel Thomas to try to democratize AI, to allow anyone who has some coding experience to quickly and efficiently become facile with deep learning techniques. So we can talk more about that at the end if you all have questions, but now I'd like to go on ahead and jump in to the Kaggle module. So sorry I didn't show that link for very long because I was trying to get logged in from my end, but the web address is at the top of the screen here if you haven't already logged in. If you have forked this kernel before, what I'm going to ask you to do now is to go on ahead and go back to this link and get ready to fork it again. Up here where it says edit for me, if you go to this page, it should say fork for you, and I want you to go on ahead and click that button. Another thing I'll ask to people out there is this button right here is the upvote button. If you would please help us out and click that button to upvote this kernel, that'll help increase the visibility in the Kaggle kernels for everyone else. And so while everybody's getting their notebook open, I'll talk a little bit about what Kaggle is. So Kaggle is a website that hosts a lot of competitions in deep learning and machine learning. And sorry, this is moving a little bit slow. Probably there's a lot of burden on the server right now because we've got a bunch of people doing this. So hopefully everyone will get their notebook open in just a minute. But the RSNA has
just one second. If people could give us a sense when they do a task, we're gonna use like the 10% rule. Just type done or just something on the Slack channel or wherever, so that we can know how to pace and not leave many people behind. That would be really helpful. Sorry to interrupt you.
Okay, no worries. Still loading here. So anyways, the RSNA for the past 2 years has hosted competitions on here, previously with chest CTs and this past year with chest x-rays, trying to get people excited and get developers interested in developing AI for medical imaging. So they have this function on their website called kernels, which allows me to set up an environment in which you can run the code without having to have any experience in setting up a development environment, without having to download any of the libraries. All the libraries for the functions that you'll use are already available to you, and that's one of the biggest advantages of using Kaggle kernels as opposed to some of the other options that are out there, which we'll talk about a little bit if we have time at the end. So once you get into this screen, here we're looking at the editing profile. So we are inside what's called a Jupyter notebook. So just to give credit where credit is due, the code and the data and the notebook were all adapted from an article that was released in the Journal of Digital Imaging last year by Paris Lakhani et al. And it's called Hello World, Deep Learning in Medical Imaging. I've tried to modify things to make sure that there's minimal effort required to get things up and running. But feel free to follow any of these links if you're interested in seeing where all of this stuff was derived from. So if you haven't already, go ahead and fork the notebook in the menu that you saw on the last page. And then if you have, then I want you to go down over to the bottom right hand of the screen and scroll down below all these different versions that you see here, below the draft environment down to settings. And I want you to make sure that GPU is turned on, because that'll speed things up when we get to training later. So everybody just take a second to try to make sure that GPU is turned on. So in the notebook, if you click in one of these cells that has a bunch of text in it, what you'll find is that the appearance changes. That's because these are Markdown cells, and so there's a combination of what's called the Markdown language and also some HTML tags that are used to format the text to make it look prettier when you run the cell. So how do you run the cell? Well, if you click inside of it, and it's a Markdown cell, you have to hit Shift and Enter at the same time. You can see that here, that instruction here, to format the cell so that you're able to see the formatted text again, and it makes it a little bit more readable for folks who aren't used to looking at HTML and Markdown. So then there are also code cells, and so when you see something with the brackets beside it and the colon here, then that is a code cell, and so these are cells that you can run. So hello world is a time-honored tradition in learning a new programming language. The initial exercise that pretty much any tutorial or book will teach you to do is how to print hello world to the output display for your programming environment. So here, what we're going to do the first time around is just type hello world exclamation point, and then to run the code cell you can either click the play button over here and you'll see it print output there, or you can do the trick from above, which is press shift and enter at the same time to run the cell from the keyboard. So I hit shift enter, you see the output there, hello world prints to the output display. And so because we hit shift enter, it moved on to the next cell, and so we'll need to format that again by hitting shift enter to make it look like it did before if you want to make it more readable. So the next thing we're going to do
We're going to pause a little bit to see some examples of the hello world.
Okay.
I just want to encourage everyone to share their hello world just so we can make sure everyone made it to the first module. And also if the shift enter is hard, then just go ahead and click that play button. That'll do the same thing. And I'm sure Walter already mentioned that.
Getting hello world right is about the extent of my programming knowledge, so pretty happy with myself that I got it to work this time.
Yeah, so while we're waiting for feedback from people, the things that can mess you up when you're editing a code cell, or if you accidentally delete one of the parentheses or delete one of the quotes on there, if you try to run this cell, you'll get an error from Python that says invalid syntax. So the problem is Python never saw an end parenthesis to terminate this command print. And so even if I put the end parenthesis on there, I still don't have the end quote, so it still doesn't know that it's time to terminate the command. So you need to have end quotes as well as in parentheses to get the output to print in the proper way.
I've gotten a few hello worlds and a
Okay.
few messages that it's working, so we can move on.
Okay, so we're just a few bits of terminology here, and don't worry about reading too much of the text in this. The idea is that once you fork this, you have a copy of this on your Kaggle account, and you can come back to this and learn more and more. You can follow the links to learn more about the different terminology that we're using and the different programming modules, libraries, types of things that we're using in this environment. You can come back later and worry about reading all the text and understanding what we're really doing. This is primarily just to get you running the code for the first time around so that you get a little familiarity with how it's supposed to work. So anyways, we're working in the Python programming language, and the first thing we need to do is let Keras, the library that we will be using to code our neural network model, we need to let Keras know that TensorFlow is what we want to use as the backend. And so this command here, I just want everybody to click inside this cell so that you can see the play button, and then just hit the play button, and you know it worked if it says using TensorFlow backend as your output. So if everybody can just take a quick second to hit the play button and make sure that the command returned is using TensorFlow backend. If you get an error at this point, it's most likely because you may have inadvertently inserted some text or deleted some text when you clicked inside the cell. So just you know, try to make sure that you're not deleting text or adding text unless we tell you to throughout the course of this module, to try to make sure that things run smoothly. So once we're done with that, we need to, so we've told Keras that this is what we want to use. TensorFlow is our backend, but then we have to import all of the modules that we need to have the functions that we need to run the code. So we go through this long series of import commands trying to pull all of the relevant modules that we need from Keras to use in this kernel. And so we're going to hit, we're going to click inside and we're going to hit play again. And once again, we should see that using TensorFlow backend output print to the display. So then the next thing we're going to do is we're going to take a look at the data. So everybody has the same structure to their Kaggle kernel if it was forked from my latest version. So these are just a bunch of commands that basically tell Python interpreter, the interpreter that's interpreting the code and running the commands for us, to print the path where the data should be found. So we're going to hit play here, and what's going to happen is we're going to see that there's a couple of files that are labeled test, and abdomen test and chest test. And then there's a directory labeled train and a subdirectory abdomen underneath it, a directory labeled train, a subdirectory chest underneath it, directory val, directory abdomen underneath it, directory val, directory chest underneath it. And so we see there's roughly 65 training data points. We have 10 validation data points, and then we have 2 testing data points. And so the importance of splitting these data sets up is that anything that your model is exposed to in the training process is not a good data point to use for validation and testing, because the model can exhibit a phenomenon called overfitting, where it picks up on things in the training data that may not necessarily generalize to the validation or testing data. And the reason it's important to have both a validation and a testing data set is that you go through a series of trying to design the right model. And so you may run a number of experiments where you expose the model directly to your training data set, but indirectly you're using that validation data set to see how that training is going. And over time, there can be a phenomenon of indirect exposure of that validation data set to the training data set, because you're optimizing the way that your model is designed and run according to the results that you're seeing on the validation data set. So you always want to have a held out test data set that the model is never trained on and that you're never using in the validation process to make sure that you're getting a good result at the end of all your training. So then in this next cell, we go through a variety of commands that are designed to set up variables that we'll use for later in the program. So we want to set paths to the directories for the training and validation data. We want to set variables for the number of samples in each data set. We want to import additional modules that we may need for certain things. And then we're going to call a few commands here to actually just take a look at some of the sample data points to see what they look like, to see what we're training with. So if you'll hit either Shift Enter, or if you click inside the cell and hit play, then you should get this output here. You should see example chest radiograph and example abdominal radiograph. So now we kind of have a sense of what we're training on. So then we're just gonna keep moving on. If you have any errors at this point, go ahead and mention them within the Slack channel, and hopefully Travis or Kirti can help you sort them out. But we're gonna kind of keep moving on because we've got a lot of territory to cover here. So the next thing we need to do is we need to do something called setting up our generators. These are data generators that take the data that's located in the data directories that we've just set paths for, and it provides a memory-friendly way of generating data for training. So that's all the generator thing means. And then the hyperparameters are the things about how we set up our data, how we set up our training, and how we evaluate our training. These are the kinds of parameters that aren't related to the model itself, but are related to how we train the model and how we set up our data and evaluate our performance. These are all the things that we're going to have to modify as well. And again, there's a lot of text here. Don't worry about reading it all. But we are going to try to experiment a little bit with some of the hyperparameters that we're using. Some people will experiment with image augmentation, others will experiment with dropout, and we'll kind of see what some of these different things can look like when we get to our end result in training. So This code just randomizes you to a group. So if you'll just hit the play button or shift enter, this one says, I've been assigned to group 2. So then here below are some instructions for what to do based on which group you've been assigned to. And this is a modification that you're going to do to a block of code like this, but in the next cell down below. Sorry, I'm flipping around a little bit fast here, but anyways, so if you're in group 1, you're going to leave all the code cell alone and you're just going to run it in its current state. But if you've been assigned to group 2, what we're going to do is remove the image augmentation parameters in the code cell with an example here of how to do that by setting all the arguments between the parentheses here in the image data generator. There's a parenthesis here and a parenthesis there. We want to set all of these to 0 except for rescale. We want to leave alone. It should still say 1 point over 255, and then so we're going to set shear range, zoom range, rotation range, width shift, height shift, and then the last one that's a little bit different is horizontal flip is going to be set from true to false. But again, this is not a functional code cell. This is just an example of how it's going to look when you're done. This is how it should look right now. So if you're making these modifications, you'll go in and you'll make sure that these parameters are set to 0, and you can see me doing this here. Yeah. And I'm going to set this to false. So what
this is just sorry Walter, just to
yeah, go ahead.
This is I was going to say this is just an example where, like, if you accidentally delete a comma or something and don't notice it, it can not work. So I would forewarn that if it doesn't work or something, always just check your commas and syntax, because I've messed up there before.
Yeah, perfect. So you want to make sure that there's a comma after every parameter except for this last one. You don't want a comma after there, because then Python interpreter will expect another input after that point. So if you're in group B, group 2, you're gonna change all these parameters to look like this. If you're not, you leave everything alone, and it should be it should look something like this here. And then you're going to run that cell, and if everything worked, you should see it print out success. So then we're going to go on to, if you've had success as your output there, we're going to go on to creating the training generator and the validation generator. And then, so click inside the cell and hit the play button or shift enter, and you should see, if it was successful, training generator found 65 images belonging to 2 classes, validation generator found 10 images belonging to 2 classes. So that's the sign that it was successful and that you haven't run into any errors so far. So then, now we've got our data generators, we're ready to construct our model. So we're going to start with a backbone that is the Inception v3 network that we talked about earlier, with weights that have been pre-trained on the ImageNet dataset, which is a common benchmark in machine learning, deep learning research, computer vision research. And then what we're going to do after this is make sure that all of the pre-trained weights in the model backbone are frozen, as in not trainable. So this line of code, or these 2 lines of code, set all of those layers to false. And the reason we do this is because these have been extensively trained, these parameters here have been extensively trained to recognize a variety of features in images that we really don't want to lose those right away. But what we're going to do is, on top of this backbone, we're going to put some custom layers designed specifically to address the task at hand, which is differentiating chest x-rays from abdominal radiographs. And so we'll make the layers in the top of the network, or the top of the model, trainable. But for the first set of training, we want the backbone to be frozen, and then later we can do what's called fine-tuning the model once we've trained the custom layers that we're going to put on top. So everybody hit the play button, and it may take a little longer to do this part, but this is just setting up the backbone for the model architecture, and then you should see output print that says model backbone initialized once that's been successful. So we'll take a second just to make sure that everybody gets caught up at this point. And if anybody's having any issues, please let us know on the Slack channel.
So as people go through this, I wanted to just remind folks of a few things from the previous journal club that you can go back and watch. So one was, how does deep learning learn? And if you remember, I said you can think about this as an onion where you're pulling back the layers, and every layer recognizes a feature. And so, for example, if you're looking at a cat, one layer may just recognize edges. Then the next layer will recognize sort of textures. And then every single layer keeps getting fed onto the next one. And finally, you end up saying, if you have these 5 things, then you're most likely going to be a cat. Or if you have these 4 things, you're most likely going to be a dog. And so if you look at the code, Walter, do you want to scroll up just a little bit for the model?
Yeah, of course.
At that point, you don't need to start training from scratch. Because these models that are released, like the Inception model here, already comes with weights. And these are pre-tested on other things, not necessarily medical imaging. And this is, you want to start from those weights. You don't want to start from scratch because you want to save your time for training and the GPU. And that's why for the last layers, then you don't want to train on the last layers because those ones you want to fine tune to the problem that you have. And the earlier layers, you're okay from it learning from the past, cats and dogs and the ImageNet sort of competition. And then also just scroll one more up. I think one other thing is just to remind you that you need to have the validation data, the training data, and the test data, and all those must be separate. And I like to think about the parameters. It's a little up, Walter. And like you're coming down a mountain. So if you like to go hiking, you go up to Mount Everest, and you need to come down, you have to figure out what's the best way to get down. And the deep learning machine will not know how to get down. So it starts at the top, says, maybe the best way to get down is a path without bushes, and just goes down. And so those are sort of like the epochs, which is the number of tries it makes, you as the mountain climber comes down, and it looks at the data and tries to penalize itself where there are many errors made, and those are the loss functions, and rewards when it makes a correct decision. And by iteratively going through these types of training is how it gets down to a good point where it gives you a high probability. So hopefully people are catching up, but I just wanted to, reiterate on some of those concepts, because as you go back to this notebook, and that's the idea, is that you're going to have a little bit of background to figure out, what things you can change, and maybe you could get a new data set and just split it in the same data and use the same kernel to train and see what's the output, and you can also change some parameters. Back to you, Walter.
Yeah, I think that's great. And if we do have time at the end, we do have a couple other content slides on the PowerPoint presentation to kind of hammer home some of those points. But main goal here is to get through the code, and then people can come back later to get a little more familiar with some of the finer points here. So the next code cell after your model backbone has been initialized is another randomization step. So if you'll go on ahead and hit play and see which group you've been assigned to, in this case it says I've been assigned to subgroup B. And so if you've been assigned to subgroup A, then you're going to leave the next code cell alone. And then if you've been assigned to subgroup B, then you're going to comment out the line of code containing dropout. So a comment in code is something that the Python interpreter is not going to interpret as a command. It's there more as breadcrumbs to help you describe to other people who are reading your code what you're doing in these steps, and also for a way for you to eliminate some of the code from being run in a sort of testing or development environment. So here if you are in subgroup B, then what you're going to do is you're either going to type the # or the hashtag, and then you don't have to put a space in there. That's a style point that I like to put a space in there. But you can just type the # or the hashtag, and that comments out that line of code, and then you can run your cell. The other thing you can do is there's a keyboard shortcut for this. So if you're on a Mac, it's Command and then /, and if you're on Windows or Linux, then it's going to be Control/. So Command/ will automatically comment out that for you as well. So I'm going to leave it alone just to show everybody what it would look like in optimal situation, but then the people who are experimenting can kind of see, you know, what differences they might have in their training from what I get as the result of mine. So then you're going to hit the play button or Shift Enter to run the cell, and what this does is it creates a series of layers on top to give a probabilistic output between 0 and 1 as to whether or not it thinks it's a chest X-ray or an abdominal radiograph. Then it puts the model, connects the model top to the backbone, and then compiles the model with an optimizer. In this case, we're using the Atom optimizer with a learning rate of 1 × 10⁻⁴, and then some of these other hyperparameters that we use to kind of play around with different features of how the model is optimized to fit the data. And then we select a loss function, and for a binary problem or an option or a problem where you're trying to classify between two different categories, binary cross entropy is the loss function that we typically use. And then for our performance metrics, we're going to look at accuracy. And so once you've run this cell, if everything was successful, it should print out setup complete to your output here. And so next we're going to set up training. And Judy mentioned a few minutes ago this concept of epochs. So an epoch is one cycle of the model over all of the training data. So you pick a batch size, which is however much you think your GPU or your CPU, depending on where you're running this, can hold in its memory at any given time. And so sometimes you have to play around with that if you're using a GPU that doesn't have a ton of memory. Here, the batch size that we've chosen should work on everybody's GPU instance that they're using. But anyhow, and then the epochs is the number of times you want to loop over that training data to try to further refine your model. So then we're going to record the history of the model, and we're going to call model fit generator, call our training generator steps per epoch. In epochs, validation data is our validation generator, validation steps, and then once all that's done, we should see that it starts training. So it takes a second to initialize, but the advantage of using the GPU is that once it starts training, it actually moves very fast.
Wow,
if you were doing this,
so much faster.
Yeah, so the past couple of times that we've done this demonstration for our co-residents at Brigham, we use the CPU function, and this step alone would take about 5 to 10 minutes. But here you can see that because we were using the GPU function, it moves very quickly, and that's because GPUs have an architecture that's optimized for doing the kinds of calculations that you need to do deep learning. And that's all I'll say for now, but suffice it to say that it speeds things up considerably. And whenever you have the ability to access a GPU, it's much better to do that and much faster. So then what we're going to do in this next cell, assuming that everybody's gotten to the training complete step, and let me actually go back for a second and talk troubleshooting. So if you receive an error message on this step, it's likely that the GPU functionality of your kernel has failed. So what you need to do is restart the kernel by going down here to this double arrow button at the bottom near the console, and just click that button to restart your kernel. When the kernel restarts, you have to go through and run every other code cell that precedes this one before you can start training the model. So that's kind of a, hopefully this doesn't happen to you, you don't have to do this, but if you run into an issue with running this cell and there's no syntax error returned, meaning that you changed some line of code to the point where the Python interpreter can't interpret it anymore, Then try restarting your kernel, running all the cells up to this point, and then see if you can get your model to train. If that doesn't work for you, then later come back to the module, just try to follow along with us for the rest of the module, and then later come back to the module, turn GPU off in the settings panel over to the right, and then that'll force the kernel to use its CPU, which will be slower, but it'll still get a result at the end. So now moving down to...
Sorry, is it okay, Walter, if you jump in and say that, you know, if you do have to restart your GPU, all those steps are actually really fast. If you just click like play, 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 or do shift enter through all of them, so you'll catch up very quickly.
Yeah. So getting down to here. So now that the training is complete, we've saved our history, and so what we're going to do is we're going to plot and evaluate the training curves for training these custom layers for the top of our model. And so on top, you should see training accuracy and validation accuracy, and on the bottom, you should see training loss and validation loss. So the loss function is something that we're trying to minimize. So what we should see is a continuous decrease in the training loss over the 5 epochs of training that we're doing. Then the validation loss, you know, may increase and decrease. Some of that's related to the fact that you're not directly training on the validation data. Others of that is related to the sort of way that the optimizer algorithm is run. It kind of generates some noise, and so sometimes you'll see fluctuations in the validation performance, but your training performance should be a pretty smooth decrease for training loss and a pretty smooth increase for training accuracy. So the next thing we're going to do, just to kind of keep moving and get through the steps, is we're going to unfreeze the model backbone to do what's called fine-tuning. So now we've trained the top layers of the model. Now we're going to go back and we're going to train just a little bit more with all of those layers in the model backbone set to trainable in order to fine-tune the model and try to get even better performance than what we got before. So let me go back one more time to this cell. So here, at the end of each epoch, we see this term validation accuracy come up. So that's how well the model performs on the validation data set at the end of that epoch. So we see 75%, 100%, 87.5, 100, 87.5. Because it's a small validation data set, only 5 of each type of radiograph for 10 total data points, some of this is probably randomness due to chance that we had an epoch where it was 100%. But it's also kind of an easy task if you think about it for us to do, and so probably also easy for one of these models to do to differentiate between a chest X-ray and an abdominal radiograph. So anyhow, that's sort of beside the point. So we want to see, you know, if we can get an even better, more consistent model. So we're going to do what's called fine-tuning. So click inside this cell, hit play. You should see setup complete. And what this does is it goes back through the model and sets all the layers to trainable. And then once you make a change to the model, you actually have to compile it again prior to continuing training. So we recompile the model with the same parameters as before. And then we can go back to setting up the number of epochs for training. So this time we're only going to train for 3 epochs. And then we're going to record the history. And so if everybody will, once again, go ahead and press play here, and you should see a similar thing play out with your output here. It'll take just a second for everything to get set up, and then hopefully you'll see it rapidly progresses through training once the GPU is initialized. So it's getting everything into memory at this point and getting the model and all the training parameters set up. And this round of training should take a little bit longer because you're training on many more layers than you trained on before. So it's a lot more parameters for the model to fit. And so it takes a little bit longer. We're not moving through these epochs quite as quickly, but it still takes a lot less time than it would with the CPU. So the first time around, the first epoch always takes a little bit longer, and then after that it takes about 3 seconds. So still pretty quick. And we can see here that with each epoch, our training loss, there's a little bit of noise there, but overall it decreases. Our training accuracy goes up, our validation loss goes down, validation accuracy is at 100% the entire time. So then we'll just take a look at what the curves look like again to give you a sense. And so here you're seeing that training loss is continuously decreasing, the validation loss is continuously decreasing, and the training accuracy and validation accuracy are both getting very close to 100%. So finally, we talked about training and validation throughout the training process. Finally, once we've fine-tuned our model and it's ready to be evaluated on the test data set, remember that we've held this test data set out and it's never been exposed, or the model's never been exposed to the test data. We're going to assess the performance and see how it does. So here in this final code cell that we're running here, we set the path to the test images and then show those images, run the model inference, and then print out the model inference next to the image. So if the model score is greater than 0.5, and remember this is a probabilistic output from the model, so if there's a greater than 50% chance in the model's eye that this is a chest-rated graph, we'll print out chest-rated graph. Otherwise, if there's a less than 50% chance, we'll print out abdominal-rated graph. So let's just go on ahead and run the cell. And it may take just a minute because, again, it's going to use this GPU to run the model. And so it takes a second to get the GPU instance initialized. But here we see a chest-rated graph. The model predicted with greater than 99% confidence that this was indeed a chest-rated graph. Here we see the abdominal rated graph, and then greater than 98% confidence that it was an abdominal rated graph, or 1 minus 0.012 is going to be greater than 98%. So at this point, we are done with our demonstration. So just to kind of go back and review, what we did was we trained an Inception v3 architecture to recognize the difference between a chest-rated graph and an abdominal-rated graph. And so what we haven't done is we haven't shown it any other types of rated graphs. So one of the important things to remember is that these models only do what you train them to do. In fact, if you were to show this model any other type of X-ray, it's not entirely clear what the output would be, but it would probably be somewhere in the middle. It wouldn't be super low, it wouldn't be super high. It would be pretty uncertain about where to classify that image unless it was a lumbar spine rated graph, and then it might put it into the abdominal rated graph category, or a pelvic rated graph, it might put it into the abdominal rated graph category. Thoracic spine, it might put into the chest rated graph category. But because we didn't specifically train it to classify those other things, it's not going to be good at doing those things. And that's a really important point for everybody to remember about what deep learning can and cannot do at this stage with these types of models. So I will open it up to Travis, Kirti, and Judy to see if they have any other points they want to add. And then I think we're getting close to time, so I have some other slides that we can go through, just kind of reiterating some of the theoretical points, or
yeah, I think
we can open up for questions.
We can go through the slides as people type their questions in the chat. Yeah.
All right. So I'm not going to click through this link just for the sake of time, but actually I will, because there are a couple of things I want to show. So Google Collaboratory is another free resource. This one requires a little bit more technical prowess to be able to use effectively. But the one thing I will point you to is that there's a machine learning crash course that Google has that I think is pretty good. It does require some prerequisites. So if you go to the website and click through some of these links, you'll find that there are actually some good links out to some different crash courses and getting started with some of the tools that you'll use. And you can really go through a lot of these links and references to learn basic Python, some of the basic libraries that you use in data science. But then once you've done the pre-work, you can go through the crash course and kind of get up to speed on using some of this some of the machine learning tools that, like the ones that we use today. So it's a good resource for some independent study. You know, you kind of have to search around to find where your experience level will take you and where you need to start. But it's a resource that I just wanted to introduce people to, just in case they were not familiar with it. So I'm going to turn it over to Kirti for this next couple of slides, just to talk about, you know, in general, what are we doing with machine learning while people are have a chance to type in some of their questions. So Kirti.
Hi, thanks so much, Walter. So I think, you know, understanding what is the theory kind of behind this and what are the sorts of problems that you can appreciate, and some of the kind of understanding those steps, I think, makes the complicated examples that much more relatable. So in terms of machine learning, what is this? And it's basically, we're just trying to teach a model automated learning of rules and patterns from the data. And there's two major categories, supervised versus unsupervised machine learning. And our example was something that's supervised. So we are giving it data, we're telling it the data that we gave to this model, we told the model whether it was a chest X-ray or an abdominal radiograph. And it trained against those labels of knowing which one it was. So that's supervised learning, where you're kind of teaching it and you're giving it the right answer as part of the learning process. And so you can use that both for classification and for regression. There's also unsupervised learning, where you're trying to cluster data. So basically the model is just trying to figure out what things are more alike versus unlike. Yeah, and there's all, you know, some of these other examples here. And then I think we can keep moving forward because these graphics, I think, are really nice and intuitive. So an example of a classification task, if you think about something simple that maybe has two features, would be these points here. And we can all appreciate this from our math background, that maybe are from two different classes. And we're trying to figure out what's the best way to separate these. And so in the most basic of terms, you can just use a straight line to separate them. And so you can see, you know, on one side where those points laid out and where the model predicted what would be the best place to separate the two classes. And this is a slightly more complicated example. So here we can't just use a single straight line, but you can use polynomial regression or something that could approximate more of a circle. And this could also give us a relatively good way of separating these two classes. I'll pass it back.
So just to show where neural nets excel, and I just saw a question about sharing the link to the Google crash course in ML modules I mentioned in the beginning. So I will share those links in the Slack channel after the session is over, and they'll be available there to you after this case. But just to show you an example of what happens when data gets a little more complicated, it's much harder for a simple model to capture the data, so we have to find a more complicated model, and that's where these neural nets come in, because it's hard for the spiral data set to draw any kind of shape with any usual function you would think of in mathematics to capture the data. But here we can set up a neural net, and I'm just adding layers and units within each layer to try to demonstrate something that's a little closer to what would be considered deep learning. And here you can play around with different activation functions, different hyperparameters to try to optimize your learning here. And then you can run an experiment and see how long does it take for the neural net to converge on a good solution. And here it's moving kind of slow. Slower than it was before, but just to show you that, like, over time, if I come back to this, you'll see that this has converged to a pretty good solution. So I'm going to skip over a couple of these for now and go to this one. So I think this slide is particularly informative because it sort of shows you, what deep learning is seeing. So you can look at each layer of the network and see kind of what the model is fitting to. In this example, where this is from 2 journal clubs ago, where they designed a model to distinguish between different phases of contrast on an abdominal CT scan. And so you see with each layer, the higher level layers are detecting higher level features like different contrasts in the image and more image related contrast and not contrast media. But then as you get lower down or deeper into the network, you get more fine-tuned features that are localizing to the IVC, that are localizing to the kidneys. And so this kind of gives you a sense of what the neural network sees. So these are just, again, hammering home the points of training a neural network model and what kinds of things we do for model evaluation. And then Travis, do you want to talk about the loss function?
Sure. Yeah. I mean, I think the key thing for me, like when I think about loss function and what you're trying to do is sort of decide how much, I guess, error. In this case, I think this model here is basically just showing like a distance from the curve, and that's sort of your error, the distance from your point from your theoretical, classification curve between the two things. I mean, the way that I like to think of it is just minimizing. Your goal is to sort of like minimize the error that you have for each data point, but also you run into the problem of like overfitting your data, which I think we talked about a little bit, but I feel like is one of the more important concepts here. If you don't do something to address, like you can't just minimize loss, totally willy-nilly, unless you have to. There are a variety of ways that Walter could describe better than me, of ways to sort of forget that loss minimization so that you don't overfit your data, and then you can't actually use your model on anything except your training set.
Yeah, so just to point to the discussion of overfitting and underfitting, there's actually a really good article on Medium that's I linked to somewhere in here talking about overfitting. I think it was in the section on the hyperparameters. Yeah, so this article here under heading 3, setting up generators and selecting hyperparameters, if you click through to this link, it's a really good discussion of overfitting and underfitting on the Towards Data Science channel of Medium, and so that's a good place to go to try to get a better understanding of what we mean when we say those things. But the last thing I'll say about the loss function is that the reason we don't use accuracy for this is because we need to be able to calculate this after every step in training. So it needs to be able to be calculated quickly on batches of data as small as even one sample, and that's really, as Travis said, you're really trying to minimize the error in the model, but the biggest trick is trying to make sure that you're able to calculate these quickly and on an individual sample. So I think we're getting pretty close to time. Do we have any questions?
So I think some of the comments I'm seeing is more like, okay, I need to go back and do this, from start to end again. And I think that's fair enough. What I would recommend is to try and get some sample data sets like ultrasounds, lumbar spines and thoracic spine, and just see how it performs. And you can keep posting your messages on the Slack channel and just go around, try it, play around with things, break things, and hopefully this was super helpful. And and I wish to thank again Walter, Travis, and Kathy, and really thank you for your time, and hopefully folks found it helpful.
Yeah, thanks for having us, guys. I would just say definitely now that we've gone through it once, just log back in, fork the kernel again, and actually just read through every one of Walter's sort of steps as he's described it. I feel like getting through it is the point of this exercise, but going through it again, I think it'll make a lot more sense the second time through.
Yeah, and I agree with Travis that the more you go through it, the more it'll make sense. I mean, that's sort of how I've learned to get to this point. And so I would just say that, this is a launch point for you, or this is what we've intended it to be, to kind of get your feet wet with coding and hopefully do it in an environment that's a little more comfortable to you, where you didn't have to set anything up to get going. And so I hope you find this helpful, and thanks again to Judy and ACR, RFS, and the AI Journal Club committee for having us. It's been a lot of fun, and I hope you all enjoyed it.
I was also happy to be here, and just think of this as the beginning of your journey or a step on your journey towards getting a greater understanding of this topic.
Oh, and one last thing, I gotta call out some other people that helped out. So Andreas Rauschaker and James Condon for giving me tips on some of the things that I could do to make this model better from earlier versions. So thanks to you guys.